Hey everyone, so this is going to be the first tutorial for CS1 that I'll be doing, and it's going to be on stacks and queues. So if you were in my sessions last semester when I was tutoring Intro to C, then you might have seen this linked list file, which I've gone over plenty of times by now. And essentially, stacks and queues are implementations of this exact linked list, and I'm going to provide this program for you guys to download in the description below. I'll most likely upload it on GitHub this time because I used to be using Mediafire and the links expire after a certain amount of time, so I think I'll be uploading my code there instead. But yeah, that's pretty much it. So we're just going to go straight into it. So the basic concept behind stacks is the principle of first in, last out. So what that means is whatever value you put into your stack is the last value that's going to come out of your stack. So just like the name implies, it gets stacked on top of one another. So here we have just an empty diagram of a stack, and you can see how it kind of builds upwards instead. Whereas when we were visualizing linked list, we kind of think of it like a disjointed array, essentially. Whereas stacks are right on top of each other. So just with this being a new data structure, it uses different function names compared to linked list. So in linked list, we have, create node, destroy linked list, head insert, print list, and then in the more advanced one, we change all of the prototypes to work with linked list instead of just nodes. So stacks is going to be very similar to how linked list.c works. And I'll also upload linked list as well, so you guys can use this for comparison. So stacks.c works very similarly in that we pass it a node instead of an actual stack. And then queues is going to work more similar to the advanced version. It's going to take a queue instead of just a node. So let's go ahead and explain the functions for stacks first. So stacks use push, pop, peek, is empty, and is full. So push is essentially the word that you use when you want to add something to your stack. So when we put something in the stack, we push it. When we want to take something off of the stack, we pop it. And then peek works very similar to pop, except instead of actually removing the element, we just return the element. So we say, okay, this is the one at the top essentially. And then is empty and is full does exactly what it sounds like. We check if the stack is empty or if the stack is full. There's multiple ways you can do it. I'm going to show you how I do it a bit later on. So here I just have an example of how this is visualized. So we have our empty stack here. And then when we push these values, so let's say we call push 1, push 3, push 5, push 7. This is what our stack looks like after all these calls. And here you can just see what's it doing. It's adding 1, adding 2, adding 3, adding 5, adding 7. So 1 was added first, and it's at the bottom, right? And we can't get to this value unless we pop 7, 5, and 3 off of our stack. So here I have 5 more commands. So we have peek, 2 pops, peek, and a push. So you can see what's happening. We print out the 7 because it's at the top of our stack. Then we pop it, which means we get rid of it. Then we pop again, so we get rid of the 5 this time. Then we peek again. We should print 3 because that's the value at the top of our stack now. And then I push 9, so I push 9 onto the stack, and now it's the top of the stack. So let's go over the functions now and how this works. So here you can see I'm going to be checking if it's full by using a defined definition for full stack. I'm setting it equal to 10. You can set it equal to whatever you want, 5, 25. And there's multiple ways you can do this, but this is how I'm going to be doing it. Then we have our node struct, which is identical to the node struct in linked lists. And this is going to be essentially the baseline for our stack. So the first 2 functions we're going to go over are is empty and is full because they're the most simple in my opinion. So is empty essentially just checks if the stack exists, right? If there's nothing at the stack, then it's empty, right? And we can just put this on the return line, right? Because conditionals will evaluate to either 1 or 0 if it's true or false. So in this case, if the stack is empty, right? If it's null, that means it's empty. So it returns 1. And obviously if it's not, if there's actual values here, then we return 0. Then is full essentially works the opposite way, except we have to check all of the positions. So we're using a temporary value to move through our stack, and we have a counter. And then we're going until essentially the counter equals full stack, which we've defined to be 10. And essentially we're saying, well, if we've shifted over 10 times, that means our stack has 10 nodes, and that means we're done, right? So obviously if we're above that, then we never will get above that, and I'll show you why. And then obviously if temp doesn't equal null, that means we keep shifting over, but if it does, that means we didn't reach full stack, so we break and then we just do return count equals full stack. Once again, conditionals will evaluate to 1 or 0. So if count equals full stack, that means our count value should equal 10, and then that should return 1 if it's full. So push, and this is what I was saying, we will never get a value above full stack, and that's because we're going to be checking if the stack is full every single time we're pushing on the value. So first I check, check if the stack is full, right? Well, I should say full stack. Right, we can't push a value onto something that's maxed. So if our stack here had a height of 4 instead, then this would be the top. We couldn't push anything above this. So we go back. Yeah, so if it's full, then we just print out the stack is full and we return. However, if it's not full, that means we can put a node on top of the stack. So here you can see that this create node looks very similar. It's actually identical to the create node function from linked list. So if I do this, you can see that the create node function here and the create node function here, let me move this, kind of get on the same line. They're essentially identical, except the next value for a linked list would be pointing to null. However, we want to shift the head essentially one position over now, because now it's underneath the node we just added, right? So now we're setting the next value equal to the top of the stack, whereas before we'd be setting it to null. And then we're just returning the stack we created. So let me put this back over here. And then pop does the opposite check. So instead of checking if it's full, we check if it's empty. And obviously we can't pop an empty stack, so we just print out we can't pop anything and we return null. Then you could return stack here, but it really doesn't matter because stack is null either way. Then we check, we have a maintained temporary value for stack. Then we print out the value at the value we're going to be getting rid of. So temp data, and then we essentially shift over stack 1. So if I were to open paint here, if I had a stack that looked something like this, so we have like 1, 2, and 3. So our stack pointer, which is going to be what I'm going to refer to as the top of the stack. So our stack pointer is here. We're setting a temporary value equal to our stack pointer. So S and T are both here. Then we're saying the stack pointer, which is the top, goes 1 under, and then we free temp, right? So this S doesn't exist anymore here. So S is underneath it, and we delete T. And then we also delete the connection. We set the next value equal to null. So that deletes the connection from T to S. And now this layer is empty again. So we can do something like that. And then we return the stack at its new head, which is this position. So that's how pop works. And then push essentially just says, okay, go to the top, put a value here, right? And keep going until you get to the top right here. So peek essentially does the exact same thing. So we check if it's empty, right? We can't peek if there's nothing there. So we essentially copy the same check, and then instead of doing any of this removal process, we essentially just print the value at the top, right? Because if it's not empty, that means there's at least one node, so we just print out that value. And then print stack, we check if it's empty, right? We can't print if there's nothing there. But if there is something there, then we copy print list in linked list.c, which looks like this, which essentially just checks if the head is null. And then if it's not, that means we have several or at least one node. So we just print out the value at that node and then shift it over by going to its next value. And also, I'm assuming you guys understand how linked lists work. If not, the video is in the description for you guys to watch. But yeah, so I'm not going to explain this too much. And then here in main, it looks complicated, but it's essentially just a menu-based program I've created so that we can test out our functions here. So I'm going to go ahead and do this example I put up here. So let's go ahead and run this. So we have stacks.c. So let's say I wanted to test out our various functions. So let me peek, right? There's nothing in the stack, right? So we can't see anything. And I put -1 as my error value. You could probably format this better to say like, oh, there's nothing in the stack, but this is how I have it. We can check if it's empty. So the stack is empty, right? There's nothing in it yet. It's not full, right? There's nothing in it. And if we print, right, the stack is empty. You can't print an empty stack. And if I popping, you cannot pop from an empty stack. But if I push, let's say I want to push the value, in this case 1, I want to push the value 3, and I want to push the value 5, and then 7. If I print this out, we see our stack, you see how it's printing backwards, right? And it matches what we have here in our input. So now let's go ahead and do these 5 inputs. So if we peek, we should get 7. If we remove, so if we pop, we should remove 7. If we remove, we should remove 5. And then if we peek, we should peek 3. So that would be 3. And then if we push 9 and then print it, we should get 931, which is exactly what we get. So I'll leave this in the description for you guys to download, and hopefully you can mess around with this and see how stacks work for yourselves. And you can format this better, but it's a very simple way that I've done it. And then obviously if you type 7, it cancels the program. So that's how stacks work. So they have this principle of whatever you put into the stack goes on top of your previous values. Well, queues are essentially lines for us in America. So it works sideways like this. So instead of putting our values on top of each other, we follow, or queues follow something called first in, first out. So just like a line for like something in an amusement park, the person who goes in first is the person who leaves first. So if I put 1 in, it goes to the front of the line. And then if I put 2 in, it goes behind that guy. And if I put 3 in, it goes behind, and et cetera, et cetera. Okay, so it follows the principle of first in, first out, right? And I'll explain what this means in a bit. And just like stacks have their own functions, so does queues. So queues have enqueue, dequeue, front, is empty, and is full, right? So these do the exact same thing. Front is just a different way of saying peek for stacks, does the same process, essentially just checks what's at the front of the queue. And then enqueue adds an element while dequeue removes an element, right? So essentially identical to stacks, just different names. And like I said, it's visualized sideways compared to a stack, which is visualized upright. So we have our front and we have our end. So if I enqueue 1, 3, 5, 7, so these are the same numbers from stacks, so you can see how they differ. You can see that my queue goes 1, which next position is 3, next position is 5, next position is 7. Then if I do the same commands except with their respective queue names, so front, dequeue twice, front, enqueue 9, we get this as our queue. And if we take a look at our stack, which had the same input, we get 139 instead of 579. So let's go ahead and explain the functions. Like I said, this is more similar to linked list advanced because they're very similar to linked list. So I went ahead and copied and changed a few things here and there. So the node function, or the node struct, stays the same. The queue struct is taken from the linked list struct, except now it also maintains the size and capacity of our queue. And obviously it's called queue instead of linked list. And then is empty just checks if the space is created for our queue. If not, right, then it's there obviously is a queue there already. And then we also check if the size is equal to 0. So size is how many people are actually in your queue, while capacity is how many people can be in your queue, if that makes sense. So is full essentially checks, right, if the size equals the capacity, that means there's no more room. So if that's true, then we should return 1. That means it's full. Otherwise, it's 0. And then create queue just sets all the default values. So just like in our create linked list, the head and tail are set to null, except we're also setting size to 0 and capacity to 10. So just like I set my stack to be a size of 10, you can also set your queue to be whatever size. And then I'm returning it, obviously. And then create node is the exact same as before, so I'm not going to explain it. Enqueue is very similar to how push works. So we check first if our queue is full, and then we insert at the tail, right? So unlike a stack, that was a pretty bad straight line, which adds on top, so it adds at the head, we want to put it on top of the head, right? In a queue, if I have it visualized going this way, so 1, 2, 3, 1, 2, 3. If I want to add at the tail. So the tail, you could think of it as the end of the line, so that's why I have it written as end here. So we put 4 here, right? So this is the same as tail insert from linked list advanced, if we take a look at that, except there's an additional check here. And we've changed also front and end to match for queue instead of being head and tail. And then also we're increasing the size. So you want to make sure you're maintaining your size throughout the entire time. Every time you enqueue, you want to increase the size. Every time you dequeue, you want to decrease the size. So here for dequeue, right, like I said, we want to decrease the size. But just like in stacks, for pop, we want to check if it's empty, because we obviously can't dequeue an empty queue. But then I'm also printing out the value here, so I'm saying, okay, this is the value that's being removed. And then I'm doing something very similar to the removal process here, where I'm essentially shifting over the value, just in case, right? So here, I'm going to remove the first position, right? First in, first out. So this value, I'm going to maintain, and then I'm going to set a temporary value to the position behind it, right? If someone in front of you leaves, now you're the person at the front of the queue. So once we free this person, we set our new front equal to the person behind us. So now where this was temp and this was front, now this is the front, so it's equal to temp. And then we essentially check to see if front is null, because that would also mean the end is null. So that's the same test case we had for stacks. And then we just decrease the size. And then front works identical to peak. We essentially just check if it's empty, right? Then there's nothing in the queue. Otherwise, we just print out what's at the front of the queue. And then the print helper works identically to the print helper in linked list advanced.c. So I recommend just checking that out again if you don't remember how this function works. But it works identically, essentially. We just pass it the queue and we pass it the front of the queue. And then the queue function works exactly the same in main as it did with stacks. So it's a menu-based program once again. And if I go ahead and compile this, it's gcc queues.c. So if I want to see what's at the front, there's obviously nothing at the front. It is empty, it's not full, and I can't print anything in my queue because there's nothing in it. And I can't dequeue from an empty queue. But if I enqueue, let's do the exact input we had at the top here. If I enqueue 1, enqueue 3, enqueue 5, and enqueue 7, and then print it out, we get 1, 3, 5, 7. And then if I copy what I had written down here, so front, dequeue twice, front, enqueue. So front prints out 1, dequeue, dequeue. You can see it's printing out what we're removing. Then I want to front again, so that prints out 5. And then I want to enqueue 9, and then print it out, and we get 5, 7, 9, and it matches what we got here. And then we can also prove, if we scroll up to when we did stacks, 9, 3, 1. So we can see the difference now between stacks and queues. And that's the basic concept for stacks and queues. There are just different ways of implementing the functions for a linked list. And there's a lot of other ways you can do these. You can have a queue that grows forever. So let's say your line doesn't ever close, right? Then your queue would essentially never be full. So things like that. But yeah, that's pretty much it for this video. I just wanted to do a quick video on what a stack is, what a queue is, and how they're visualized and how they're different from linked lists and from each other. So yeah, I hope that's helpful. I recommend if you have questions on like dynamic memory or 2D arrays, things like that, to watch my previous video. And yeah, that's about it. Thank you guys so much for watching, and I wish you best of luck for your exam.